In Chapter 2, we'll cover program correctness and efficiency. Now, the objectives of this chapter are the following: to understand the differences between the three categories of program errors, to understand what it means to throw an exception and how to throw an exception in a function, to understand the effect of an uncaught exception and why you should catch exceptions, to learn how to catch and process exceptions, and to understand different testing strategies and when and how they are performed. We also want to learn how to write special functions to test other functions and classes, become familiar with debugging techniques and debugger programs, be introduced to the process of program verification, the use of assertions and loop invariants, and to understand the meaning of big O notation and how it's used to analyze an algorithm's efficiency. So we'll start with program defects and bugs. Now, defects can occur in software products after they're delivered and can produce undesirable and sometimes disastrous results. I think we've all used established software products that occasionally have errors. Now, testing is used to show that the program's correct, but it's difficult to determine how much testing needs to be done. And this is a very important point. Testing can never demonstrate the complete absence of defects. Okay, think about that again. So testing can never demonstrate the complete absence of defects. Now, complete testing in some environments is very difficult. In missile control software, nuclear power plant controls. Now, the term bug is used to refer to software defects. Some people think that term trivializes the significance of bugs in software. Debugging is the term for removing defects, and a debugger is a testing tool that helps you find these defects. I hope you've learned how to use a debugger in your prior class, and I'm going to encourage you to learn to use that this semester. If you haven't, I think that's a very valuable tool that you want to know how to use. Now, it's much easier to eliminate defects by careful design than it is through testing. Now, you may encounter three kinds of defects or errors. There are syntax errors, runtime errors, or exceptions, and logic errors. Now, syntax errors are mistakes in using the grammar or the syntax of C++, and the compiler detects most syntax errors during compilation. So here's some common syntax errors that you probably have some experience with. Let's look at these. We've got omitting or misplacing braces that bracket compound statements. You've probably all written maybe an if statement and forgotten to surround the compound statements in the true part of your if statement, and that can cause a problem. Let's see, invoking a member function that's not defined for the object to which it is applied, not declaring a variable before using it, providing multiple declarations of a variable, not assigning a value to a local variable before referencing it, and not returning a value from a function whose result type is not void. So there's some examples of some syntax errors. Now, the compiler may not detect some syntax errors that are a result of typographical errors. For instance, here's another one you may have used. So C++ uses the single equals sign for assignments, but the double equals is the equal to comparison operator. So they're both valid syntax, but the semantics and the meaning is different. So in the case of if you use an equals instead of the comparison, then you'll just make an assignment statement, and perhaps that'll evaluate to true, and the compiler will accept it and do what you told it. It doesn't know what you meant. So a program can be syntactically correct, but still have errors. So we need a careful review, and testing are essential. So just because a program compiles doesn't mean it's correct. Now, runtime errors occur when the program's running. The runtime errors occur when the computer or the C++ runtime library detects an operation that it knows to be incorrect. And most runtime errors cause the operating system or the runtime library to issue an error message and halt the program. And different computers and operating systems and compilers handle these errors differently. So here are some runtime errors. Divide by 0, An array index out of bounds. That's when we attempt to access an array with an index value that's greater than the array's size, and C++ doesn't detect that. Null pointer reference is when we attempt to dereference a pointer whose value is null. Now the C++ standard states that the result of a division by zero is undefined. So the standard doesn't specify exactly what the compiler or the runtime system or doesn't require them to detect it, and it may vary by the computer, operating system, or compiler. So if we have a statement like this in our program, and if count is currently equal to 0, then under Windows it'll cause a divide by 0 error, and you'll get this kind of an error message. So it will tell you integer division by 0. Now under the Linux operating system, you'll just get floating point exception. Now you can be defensive in your programs and try to guard against this. So for instance, if you have a statement like this, then what you need to do is check, and if count is equal to 0, then set average to 0, else go ahead and perform the division operation. Now, since division by 0 errors occur in integer division, you could cast the int value in sum to type double before doing the division, and on an x86 architecture, average is assigned a special value representing either positive or negative infinity, depending on the size of sum. Now, for array index out of bounds errors, C++ doesn't check the validity of array subscripts. Let's see, you might ask, why doesn't it do that? It's performance. It's an extra expense to do that check every time you do an array reference. So attempting to access or modify an array element using a subscript that is negative or greater than or equal to the array's length is also an undefined condition. So as an example, if we have an integer array scores that holds 500 integers, and we use a subscript variable score sub I, where I is less than 0 or greater than 499, it'll do the calculation and try to access a memory outside of the bounds of that array, and it's undetermined what will happen. If that location happens to be a location not accessible to the program, an error could be reported. Otherwise, the program may execute, but what happens is indeterminate. We might get some errors. We might get some incorrect calculations. Depending, we might just go out and read some values, that were never intended to be in the array, and so we may get bad results, and we may not even know it. So incorrect loop control parameters. If we have a for loop and we index and count through the array, if we set up our for loop incorrectly, we might have an out of bounds error. So we need to carefully check the boundary values for an index. That is also a loop control variable. So this is an important recommendation that you can think about when you write programs that have for loops. Now, a common error is using the array size as the upper limit rather than the array size minus 1. Since C and C++ use zero-based array indexing, the first element of the array is 0, and the last element in the array is array size minus 1. Okay, so here's a for loop where we initialize I to 0, and we check if I is less than or equal to x underscore size, which is the size of the array, and then we increment I at each iteration of the for loop. Then we go ahead and we set a value in the array equal to this calculation. And here we're going to get an array index out of bounds on the very last step, because we'll be indexing one location past the end of the array. So what we need to do is have any of these three options would correct the problem. We should start at 0 and have less than size instead of less than or equal. Or we could change it, start at 0 and say less than or equal to x size minus 1. Or we could start I at 0 and increment it 1 by 1, and then we'll stop when it's equal to x underscore size. Now, parameters passed to a function could include the position and a new value of an array of a value of an element in an array. So you can have an if statement to validate that the index is in bounds, and you can return a Boolean value indicating whether or not the value was changed. So if we have a function set element of x where we take in an index integer and an integer value, then this code checks to see if the index is within a valid range of our array locations. So it sees if it checks if it's greater than or equal to 0 and less than x underscore size. If it is, then we'll update our array with the value and we will return true. Otherwise, we return false. This avoids that out of bounds error. Now, when parameters are passed to the main function, then we can access them in an array of strings called argv. And the number of arguments passed to the main are stored in a variable argc. Now, when we typically run a main program, the name of the file that we're executing is passed as the first parameter, and it's stored in argv sub 0. And then any parameters we include on the command line or in your, however you enter them into your IDE, then they're passed to the program starting at argv sub 1 for as many parameters as we provide. So if we write a main function and we expect to pass a parameter, a file name as a parameter, then we'll expect argc to be set to 2. That'll include both, the name of the file that's executing and then this file that we enter onto the command line. And so here we're doing a condition to make sure that argc is greater than 1. By being greater than 1, we know that at least one parameter was added on the command line, and then this program goes ahead and assumes that the first parameter, the first string that was entered, is the input file name. And in the case if argc is not greater than 1, that would mean no parameters were entered, and then phone.dat is a default parameter. Now, a program style comment. We saw this example where the set element of x function returned a Boolean result to indicate whether or not we were able to insert that element into the array, and then the caller of the function used that result perhaps to display an error message to the user if desired. So here's an if statement that the caller of set element of x can use. They can call this function. If that function returns false, then this if statement will execute this body and print out an error message. Now, why might we return a result? The reason we might turn this a Boolean result is we'll let the caller decide what to do under some error condition instead of doing it within the routine. Now, why might we do that? If this is a useful routine and more than one other function is calling it, then it might be nice to let whoever's calling the function, they can decide what to do in case of errors. Maybe they want to output a message to the screen. Maybe they want to halt the program. Perhaps they can just automatically continue and take another path. Maybe they have another choice. So you can give flexibility to the caller to handle errors in different ways as opposed to handling it directly in that routine. Now, finally, a pitfall. There's a kind of security vulnerability called a buffer overrun, and it's a kind of array index out of bounds error. And a common way this happens is some malicious program can send a large amount of data to a program that doesn't check to see if that data fits into the array that's allocated. I mean, sometimes web forms might be prompting for a zip code and assume that the user types in a 5-digit zip code. And if the program isn't careful, then an attacker can enter, a large amount of data and potentially overwrite part of the memory of this operating program and can cause the program to take a different path than it might otherwise, perhaps just crash the program. And in some of the more sophisticated settings, the attacker can actually inject data in such a way that it's malicious code, and the attacker can cause that to be executed and do some very dangerous things. So come and take my senior level security class, and we'll learn in detail about buffer overruns, and you can even learn how to do some simple examples. And by seeing how this works, that can make you a lot more aware as a programmer the kinds of things you need to do so that you can defend against these significant attacks. Now, if you attempt to dereference a null pointer, then the operating system generally issues an error and stops the program. Under Windows, you'll see this error message. Under Linux, you'll usually get a segmentation fault. So you can avoid this kind of error that halts your program by checking to see that a pointer is not null before you dereference it. So here's some code that will generate a runtime error. So here we declare P is a pointer to a double, and we set it equal to no, and then if we go ahead and try to set P equals 15.5, P isn't referring to a location where we can store a double. Since it's null, the program has no other choice but to halt. So you can avoid this by resetting P to reference a memory cell that can be used to store a double. So here we can declare P, then we've got to allocate space to hold a double and assign that to P. So P now points to a memory location where we can store a double, and now we can assign that 15.5. Now, logic errors occur when the programmer or analyst makes a mistake in the design of the class or the class function. Maybe he's implemented an algorithm incorrectly or uses an incorrect algorithm. So the C++ code, it may compile and run, but it won't meet the specifications and will get incorrect results. So most logic errors, they don't cause syntax or runtime errors, so they're difficult to find. We have to do testing and look at the output and determine if we're getting the results we expect. So test cases can help you find these logic errors, and that lets the programmer compare program output to the expected results. Software professionals must be diligent in detecting and correcting logic errors. So good software testers are very valuable to companies, and this is a skill that you can take and use, and that's very important. Now, here's some examples of some significant logic errors that have occurred in the past. So the original Mars lander spacecraft crashed because of inconsistent calculations, I guess using feet versus meters. Billing programs have sent out bills for exorbitant amounts of money. You may have read about some of these in the newspaper. ATM programs and off-track betting programs have caused machine owners to lose significant amounts of money. Many popular operating systems have been released with bugs that have let hackers access computers easily and illicitly, sometimes using these buffer overflow attacks I just mentioned. A popular word processing program was integrated with a document management system and ate documents off the server. In the 1980s, several patients died after software controlling therapeutic radiation machines gave them massive overdoses. In 2004, 2 automobile recalls that could have led to fatal accidents occurred because of software errors in control systems. So when you're writing software for life-critical or financial applications that have cover large amounts of funds, then software errors can, your software with bugs in it can make the front pages of the newspapers, which is not a good thing. And that brings us to the end of this slidecast.